At 15, why is it constant again?
Say it again.
At 15, why is it straight line again? Vertical line?
It's not constant. It's a stepwise function. It's a step, right?
Yeah, but
Okay.
okay. But on the graph, it shows like
It's
vertical
not
line.
necessary. It's only the same position. Same position, but the stresses, there's a step up.
Okay, I see. And
Okay.
in the
That is because the thickness change, right? From 160 millimeters to 40 millimeters.
okay, in let's say like in real life, would this like a screw or something? Would it be somewhere in between or
Say it again.
like in? I know this is like on graph, but in real life, would it be like somewhere in between the real value? The real value?
No, it's like
Mm,
that. We calculate the higher value. We
okay,
calculate the higher value. Remember, I say use the smaller thickness. Yes.
okay,
There's no point calculating this value, right? Waste time.
yeah, makes
But
sense.
because we're going to draw the distribution, we need to label them. Okay.
Okay, thank you.
Any other question? Okay. If not, so this example, it happened to show that the current structure geometry, the tail max occur at the centroid. Okay. Like when we are deriving also, when we are deriving the function, okay, last week, right? When we are deriving this function last week, right? The tau max also occur at where? The tau max also occur at the centroid. So we did write that the maximum, the tau max, right? The tau max, this is last week. Tau max occur at the geometric centroid. Now, I'm going to show you an example where this is not true. And this is not true when your thickness is not constant. I repeat again, this is not true when your thickness is not a constant. Okay, so that brings us to our next example now. And I want you to observe this. This is a very interesting problem. Okay, so let's go into example number 2. Let's get okay. As I said, you have all this. So this is, if you look at this question is a bit challenging, but not impossible. Okay. For a beam having the cross section shown, determine the largest allowable vertical shear if the shearing stress is not to exceed 60 megapascal. Okay, so the shear. So now, why this problem is so exciting? And this problem really highlight the understanding of the equations of the shear stress equation. Let's see what we have. So we know that so let's label this first, our transformation. This is our y, this is our z, this is rotation about x axis, and this is the cross section view. Okay, now gxy is equal to vy over izz qz over t. Okay, and we are given that tau max can be equal to 60 times 10 to the power 6 Pascal. Okay, we are given that value. And now we have to find what is Vy. Okay, Now we have to find Vy. So now, if we look at the equation in the box, right? We look at this equation in the box. Vy is a constant. Izz is a constant. Only Qz and T changes. Now, there are two possibilities where tau max to occur. Okay, so tau max can occur based on two possible conditions. What are they? Okay, so number one, tau max is equal to Vy over Izz. Q max, Qz max divided by T. Right? The new, so Vy over Izz is constant, regardless of whichever point that we are analyzing. But there's a possibility for tau max to occur when the first moment of area is at a maximum. Okay. The other possibility, number two, is tau max can occur when Vy over Izz is a constant. And then you have a Qz, but now the denominator is a what? Is a T mean. Okay, where now the denominator is a T mean. Okay, so the Q over T ratio, okay, the Q over T ratio is what we have to take note. Okay, which one give us the highest Q over T ratio will give us the highest tau max. Okay, so you guys say, so we will say, why is that? Why is it so confusing? So let's look at this problem now. Okay, so let's look at this problem now. Okay, so we realize that this problem over here. Let me do another one. Wait, let me see. Do I have a bigger figure? No. Let me get from a book bigger figure because I need a bigger figure to explain. Pardon me, okay? Okay, I got it. Let me start a new page on this. Okay. Okay, so so if we look on based on the two conditions, okay, so condition number one, tau max or I'll put condition number one, tau max occur when Q max or at Q max over T, right? So where is Q max? That means the highest first moment of area, which is for this case, is exactly at the what? Okay, exactly at the centroid. Why? Because at the centroid, the first moment of area is the most. Look at the first moment of area. It has the most. Okay. Or condition number 2, right? So condition number 2, come on. It can also occur where tau max occur at a certain Q value over what? T mean. So where it will be? Is it going to be at point A, where you have T mean, or is it going to be at point B? Anyone? Point A or point B? Both of them got T mean, but which one will induce the tau max? Anyone want to make a guess? Point A or point B? And you have to tell me why.
Gonna say probably point B
Why?
because it has a larger Q.
Yes. Okay. The first moment of area is bigger. Can you see my screen? Yes or no?
Yeah, we can see it.
Okay. I thought something happened. So when this is the case, we know we'll be at point B. Why will be the point B? The QZ at point A is smaller than the QZ at point B. Can you see that? Right. So you have to, it's not the maximum, but it's the greater area. Okay. So the next point we have to check at this location over here. Okay. We have to check at this location over here. Okay. We have to check at this location at point B. Okay. So the area that we're going to consider is up to here. Not the biggest area, okay, relative to the centroid, but because it has a smaller what? It has a smaller thickness for that reason. Okay, so from here, the formula that we're going to apply is still shear stress, right? Is still equal to shear stress is equal to Vy over Izz, right? Qz divided by T. Okay, so we are going to find our first moment of area first. So we are going to determine Izz. So we know that this is the width, and then this over here is our depth. Okay, so Izz. So what I'm going to do is I'm going to look at the whole structure, and then I'm going to take away the two smaller boxes. Okay, for the first moment of area. So that is what I'm going to do. Okay, so the width is equal to 50. The depth, so it's equal to 120 cube over 12, right? Minus twice, one for the top square, one for the bottom square. The width is 30. The depth is also 30. About 3 divided by 12 plus the area of the square plus by the centroid. So we know the distance from here to here for this is 15, right? And then plus 20. So 20, where 20? Because this is where the 20 is. Okay, so 20 plus by 15. And then the whole thing squared. Okay, so this will be equal to 120 power 3 times by 50 divided by 12 is 7.2 times 10 to the power 6 minus 20 plus 15 squared times by 30 times by 30 plus by 30 power 4 divided by 12 equal times 2, 2.34. Okay, and this whole thing is equal, hold on, 35 squared times by 30 times 30 plus 5. 2.34. So 7.2 minus 2.34 is equal to 4.86.